10 strangest things in the universe. Imagine standing at the edge of existence itself, where everything you thought you understood about reality dissolves into impossibility, where stars collapse into points of infinite density, where invisible forces tear galaxies apart, and where the very fabric of space and time twists into shapes that defy comprehension. The universe is not the orderly, predictable place we once imagined. It is stranger, more unsettling, and more magnificent than our wildest dreams or darkest nightmares could ever conjure. Tonight, we're going to journey together through the cosmic abyss to witness 10 phenomena so bizarre, so fundamentally alien to our everyday experience, that they challenge the very foundations of what we believe is possible. But I need you to ask yourself something before we begin. Are you prepared to have your understanding of reality fundamentally altered? Because once you peer into these cosmic mysteries, you can never see the universe the same way again. Let's start with something that has captured human imagination for decades. Something so extreme that it represents the ultimate point of no return in our universe. Picture this, a region of space where gravity is so intense that nothing, absolutely nothing, can escape its grasp. Not matter, not light, not even time itself flows normally near its boundary. We call these cosmic monsters black holes, and they are perhaps the most terrifying and fascinating objects in existence. But here's what most people don't realize, the part that should make your skin crawl with a mixture of fear and wonder. If you were to fall toward a black hole, your experience would be radically different from what an outside observer would see. This isn't science fiction. This is documented, calculated reality based on Einstein's equations. From your perspective, as you cross what scientists call the event horizon, the point of no return, you might not even notice anything particularly unusual at first, especially if the black hole is supermassive. You'd simply pass through an invisible boundary, still able to see the universe you left behind, still experiencing what feels like normal passage of time. But here's where it gets deeply unsettling. To anyone watching you from a safe distance, you would appear to slow down as you approached the event horizon. Your movements would become more and more sluggish, your light would redshift, stretching toward deeper and deeper shades of red, and you would appear to freeze at the boundary, never quite crossing it, your image fading slowly over eons as the photons carrying your last moments stretch to infinity. You would be caught in two realities simultaneously, one where you've fallen in, and one where you never quite do. Ask yourself this, which version is the real you? The one experiencing the fall, or the one frozen forever at the edge? But it gets stranger still. Once past the event horizon, you wouldn't be able to escape even if you traveled at the speed of light directly away from the center, because space itself is falling inward faster than light can traverse it. Think about that for a moment. We often imagine black holes as objects with strong gravity that pulls things in, but the reality is more disturbing. Inside the event horizon, all paths through space-time lead inward. Trying to escape would be as futile as trying to travel backward in time. In fact, inside a black hole, the direction toward the singularity, the infinitely dense point at the center, becomes a direction in time, not space. You are not falling toward the center. You are falling into your own future, and that future inevitably ends at the singularity. Now, here's a question that haunts physicists. What happens at the singularity itself? Our mathematics breaks down completely. General relativity, the theory that predicts black holes in the first place, tells us that matter is compressed to infinite density in zero volume. Infinity appears in our equations, which is usually nature's way of telling us we're missing something, that our theories are incomplete. Some physicists speculate that quantum mechanics, the physics of the very small, must somehow take over at these extreme conditions, preventing true infinities. Perhaps the singularity is actually a region of extremely warped spacetime rather than a point. Perhaps it's a gateway to another universe, though this remains pure speculation. Or perhaps, and this is the most unsettling possibility, perhaps it truly is an endpoint, a place where the laws of physics cease to have meaning, where existence itself terminates. Black holes come in different sizes, and this matters more than you might think. Stellar mass black holes, formed from collapsed stars, are typically just a few miles across. But at the centers of most galaxies, including our own Milky Way, lurk supermassive black holes, monsters containing millions or even billions of times the mass of our Sun. The black hole at the center of our galaxy, called Sagittarius A star, has a mass of about 4 million suns. In April 2019, humanity achieved something remarkable. We captured the first actual image of a black hole's shadow, the dark circle surrounded by glowing hot gas, in the galaxy M87. That black hole contains 6.5 billion solar masses. Its event horizon is larger than our entire solar system. Let that sink in for a moment. An object so massive that its point of no return encompasses a region larger than the orbit of Neptune. Here's something that will make you reconsider the night sky. We now know that stellar mass black holes are relatively common. Our galaxy alone likely contains hundreds of millions of them, invisible, silent, wandering through space. Right now, at this very moment, there could be black holes passing through the outer reaches of our solar system, and we would never know unless we happen to see their gravitational effect on something nearby. Have you ever wondered if one might be heading our way? The probability is infinitesimally small, but not zero. Space is vast, and these cosmic predators are difficult to detect when they're not actively feeding on nearby matter. But as strange as black holes are, they're just the beginning. Let's talk about something even more mysterious, something that makes up most of the universe but has never been directly detected. I'm talking about dark matter and dark energy, the invisible scaffolding and the mysterious force that together comprise 95% of everything that exists. Think about that statistic for a moment. Everything you've ever seen, every star in the sky, every planet, every human being, every atom in your body, all of that is just 5% of the universe. The rest is something else entirely, something we can't see, can't touch, and barely understand. Dark matter was first hypothesized in the 1930s when astronomer Fritz Zwicky noticed something impossible. Galaxies in the Coma cluster were moving far too fast. Based on the visible matter he could observe, these galaxies should have flown apart long ago. The gravity from stars and gas wasn't nearly enough to hold the cluster together. He proposed that some invisible matter, dark matter, must be providing the additional gravitational glue. For decades, this remained a curious anomaly. Then, in the 1970s, astronomer Vera Rubin made observations that would revolutionize our understanding of the cosmos. She measured the rotation speeds of galaxies and discovered something profoundly strange. Imagine a merry-go-round. The closer you are to the center, the slower you need to move to maintain your position. The farther out you go, the faster you must travel to keep up with the rotation. Galaxies should work the same way, with stars near the edge orbiting more slowly than stars near the center. But that's not what Rubin found. Stars at the edges of galaxies were moving just as fast as stars closer to the center, sometimes even faster. This should be impossible based on the visible matter. The only explanation that makes sense is that galaxies are embedded in massive halos of invisible dark matter, extending far beyond the visible disk. These halos contain more mass than all the visible stars combined, and their gravity is what keeps the outer stars moving so quickly. Since then, we've found dark matter's fingerprints everywhere we look. When we observe galaxy clusters, the largest structures in the universe, we can use a technique called gravitational lensing. Massive objects bend spacetime, and this bending causes light from distant galaxies to curve around the massive object like water flowing around a rock in a stream. By studying how light is distorted, we can map where the mass is, and again, we find far more mass than we can see. The invisible outweighs the visible by a factor of about 6 to 1. But here's what should keep you up at night. We still don't know what dark matter is made of. Scientists have proposed numerous candidates. WIMPs, or weakly interacting massive particles, were favored for years. Hypothetical particles that barely interact with ordinary matter except through gravity. Massive detectors have been built deep underground, shielded from cosmic rays, waiting to catch the rare interaction of a dark matter particle with normal matter. So far, Despite decades of searching, nothing conclusive has been found. Other theories propose axions, extremely light particles that would exist in enormous numbers, or even primordial black holes formed in the first moments after the Big Bang. Some physicists have even suggested that dark matter might not exist at all, that perhaps our understanding of gravity itself is wrong and needs to be modified on galactic scales. This seems less likely given how well dark matter models fit observations, but it remains a possibility. Ask yourself this: how can something make up most of the matter in the universe and remain completely invisible to all our instruments? What does it mean for our place in the cosmos if we can only directly interact with a tiny fraction of what's out there? Are we living in a thin layer of visible matter floating in an ocean of invisible substance? And if dark matter is mysterious, dark energy is downright baffling. In 1998, two teams of astronomers made a discovery that shocked the scientific world. They were studying distant supernovae, stellar explosions so bright and uniform that they can be used as cosmic measuring sticks. By comparing the apparent brightness of these supernovae to their actual brightness, astronomers can calculate their distance. What these teams found defied expectations. The universe's expansion is accelerating. Galaxies are not just moving apart, they're moving apart faster and faster as time goes on. This should not happen. After the Big Bang, the universe began expanding, and gravity should be slowing that expansion down, like how Earth's gravity slows a ball thrown upward. But something is counteracting gravity on cosmic scales, pushing galaxies apart with ever-increasing strength. Scientists call this mysterious influence dark energy, and it comprises about 68% of the total energy content of the universe. We have no idea what it is. The leading explanation is that it's a property of space itself, that empty space has a certain amount of energy, called vacuum energy, and as the universe expands and creates more space, there's more dark energy, driving faster expansion. But when physicists try to calculate how much vacuum energy there should be based on quantum mechanics, they get an answer that's wrong by a factor of 10 to the power of 120, possibly the worst prediction in the history of physics. Some cosmologists speculate that dark energy might not be constant, that it could change over time. If it strengthens, the universe could end in a big rip, where the acceleration becomes so extreme that eventually galaxies are torn apart, then solar systems, then planets, then molecules, then atoms themselves, until the very fabric of space-time shreds. If dark energy weakens or reverses, the expansion could slow, stop, and reverse, leading to a big crunch where everything collapses back together. The fate of the universe hangs on the nature of this mysterious force, and we're essentially groping in the dark, trying to understand it. Now let me tell you about something that seems to violate our intuitions about how reality should work, a phenomenon so strange that Einstein himself called it spooky action at a distance, and refused to believe it was real. I'm talking about quantum entanglement, one of the most profound and bizarre features of quantum mechanics. Here's the basic idea, and I want you to really think about what this means. When two particles interact in certain ways, they can become entangled, linked together in a manner that transcends ordinary space. Once entangled, measuring a property of one particle instantaneously affects the other, no matter how far apart they are. Not almost instantaneously. Not with some tiny delay. Instantaneously, faster than light, violating what we thought was a cosmic speed limit. Let me paint you a picture to illustrate how deeply weird this is. Imagine you have a pair of entangled particles, let's say electrons. You keep one on Earth and send the other to a planet orbiting a star in the Andromeda galaxy, 2.5 million light-years away. Quantum mechanics tells us that before you measure them, these particles don't have definite properties. An electron can spin in different directions, but an unmeasured entangled electron exists in a superposition, simultaneously spinning in all possible directions at once. The moment you measure your electron on Earth and find it spinning one way, the electron in Andromeda instantly, across 2.5 million light-years, assumes the opposite spin. Not because some signal traveled between them. There is no signal. The particles are connected in a way that transcends space itself. Einstein proposed this as a thought experiment in 1935, along with Boris Podolsky and Nathan Rosen, in what's called the EPR paradox. He was trying to show that quantum mechanics must be incomplete, that there must be hidden variables, unknown factors that determine the particle's properties in advance. Surely, Einstein argued, particles must have definite properties whether we measure them or not, and the appearance of instantaneous connection must be an illusion. But in 1964, physicist John Stuart Bell developed a mathematical theorem that could test whether hidden variables could explain quantum mechanics. Experiments performed since then, with increasing sophistication, have consistently shown that Bell's inequalities are violated. The universe really does work this way. Entangled particles are genuinely connected in a non-local way that has no classical analog. This raises profound questions. What does this tell us about the nature of space and time? If particles can be correlated across vast distances with no delay, what does that mean for our understanding of causality and locality, the idea that objects are only directly influenced by their immediate surroundings? Some physicists interpret this as evidence that space-time, the stage on which physics plays out, might be emergent, arising from something more fundamental. Perhaps at the deepest level, the universe is not made of particles moving through space, but of information, of relationships, and space is just how those relationships appear to us. Here's something that should make you pause. Quantum entanglement is not just a theoretical curiosity. It's real and it's being harnessed. Scientists are developing quantum computers that use entangled particles to perform calculations impossible for classical computers. Quantum cryptography uses entanglement to create theoretically unbreakable codes. We are building technologies based on this spooky action at a distance, even though we don't fully understand what it means about the nature of reality. Does that make you uneasy? It should. We're manipulating the fabric of reality in ways that our intuitions cannot grasp. Let me ask you something. If entangled particles can affect each other instantaneously across any distance, what does that say about the separateness of objects in the universe? Are we all connected in ways we don't perceive? Some interpretations of quantum mechanics suggest that the entire universe might be in some sense entangled, that everything is connected to everything else through quantum correlations. You and I, the Earth and distant galaxies, all linked through invisible quantum threads woven in the first moments of the Big Bang. This isn't mysticism. It's a legitimate, if speculative, consequence of taking quantum mechanics seriously. Now, let's turn our attention to objects that are almost as strange as black holes, but in entirely different ways. Imagine taking a mass greater than our Sun and compressing it into a sphere just a few miles across. Not into a black hole, but into something that still has a surface, something you could theoretically stand on if you could survive the experience. These objects exist. They're called neutron stars, and they represent matter in one of the most extreme states possible. When a massive star runs out of fuel, it can no longer support itself against gravity's crushing pull. The core collapses in a fraction of a second, and electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. The collapse halts when the neutrons themselves are packed as tightly as particles in an atomic nucleus. What remains is a neutron star, a city-sized sphere containing more mass than the Sun. The properties of neutron stars are mind-bending. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth, more than all the cars on the planet combined. The gravity at the surface is approximately 200 billion times stronger than Earth's. If you somehow stood on a neutron star, you would be instantly flattened into a layer of atoms just a few atoms thick. The mountains on a neutron star surface, irregularities caused by the stresses in the crust, are only millimeters high because gravity is so powerful that it crushes any significant deviations. And many neutron stars spin, some of them hundreds of times per second, with their surface moving at a significant fraction of the speed of light. Some neutron stars are pulsars, lighthouses of the cosmos that emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like searchlight beams. If Earth happens to be in the path of the beam, we detect regular pulses of radio waves or other radiation with clockwork precision. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and the regularity of the pulses was so precise that the researchers half-jokingly considered whether they might be signals from an alien civilization. They even temporarily designated the source LGM-1 for Little Green Men. But as more pulsars were discovered, it became clear they were natural phenomena. Today, we've detected thousands of pulsars, and they serve as cosmic laboratories for studying matter under conditions we can never reproduce on Earth. But some neutron stars are even stranger. Magnetars are neutron stars with magnetic fields so intense they defy comprehension. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. A magnetar's field is 1,000 times stronger still, a quadrillion times Earth's magnetic field. This is so powerful that the very structure of spacetime is warped by it. If a magnetar existed within 1,000 kilometers of Earth, it would strip the information from every credit card and hard drive on the planet. From halfway to the moon, its magnetic field would be lethal, disrupting the electrical activity in your nervous system and the molecular bonds in your body. Magnetars occasionally experience starquakes, where the ultra-dense crust of the star cracks and shifts. When this happens, the magnetic field lines snap and reconnect, releasing more energy in 1/10 of a second than our sun produces in 100,000 years. In 2004, a magnetar designated SGR 1806-20, located 50,000 light-years from Earth, experienced such an eruption. The burst of gamma rays and X-rays was so intense that it measurably affected Earth's ionosphere, despite the enormous distance. If that magnetar had been just 10 light-years away instead of 50,000, the radiation would have triggered a mass extinction on Earth. Think about that the next time you look up at the night sky. These cosmic engines of destruction exist, spinning silently in the darkness, and occasionally they detonate with the power of thousands of supernovae concentrated into a fraction of a second. Here's a question for you. What is it like inside a neutron star? We can observe the surface, measure the mass and rotation, but the interior remains largely mysterious. The outer crust is thought to be a crystalline lattice of nuclei packed into a sea of electrons. Deeper down, neutrons become free, creating a superfluid, a liquid with zero viscosity that flows without friction. Deeper still, conditions become so extreme that we're not sure what happens. Some theories predict strange quark matter, where the neutrons themselves break down into their constituent quarks, creating a liquid of up, down, and strange quarks. Some physicists speculate that the cores of the heaviest neutron stars might contain exotic states of matter that exist nowhere else in the universe. Others wonder if there's a maximum mass for neutron stars, beyond which they must collapse into black holes, and what happens right at that boundary. Speaking of mysteries, let me tell you about something that was discovered because galaxies are not behaving the way they should. There's a region of space, hundreds of millions of light-years away, where something massive is pulling on our galaxy and millions of others. We can't see what it is. We call it the Great Attractor, and it's one of the most intriguing mysteries in cosmology. In the 1970s, astronomers noticed that the Milky Way and other galaxies in our local region of the universe are all moving in a particular direction at about 600 kilometers per second, in addition to the general expansion of the universe. Something out there, something enormous, is gravitationally attracting our galaxy and everything around us. For years, the Great Attractor was difficult to study because it lies in the direction of the galactic plane, the disk of our own Milky Way. When we look in that direction, we're looking through all the dust, gas, and stars of our galaxy, which obscures our view of the distant universe. It's like trying to see through a forest. The trees block your view of what lies beyond. But using specialized telescopes that can peer through the dust by observing in infrared and X-ray wavelengths, astronomers have started to map the region. What they found is even more complex than expected. The Great Attractor appears to be a region containing a huge concentration of mass, including several large galaxy clusters. But there's more. Beyond the Great Attractor lies an even larger structure, the Shapley supercluster, containing thousands of galaxies and exerting an even stronger pull. Our motion is influenced by both. In fact, Our galaxy is part of a massive flow of galaxies called the Laniakea supercluster, meaning immeasurable heaven in Hawaiian. This supercluster contains 100,000 galaxies, including the Milky Way, all being pulled toward these massive attractors. Here's what's unsettling. We still don't have a complete picture of what's pulling us. The region is so obscured and complex that mysteries remain. Could there be something unexpected there? Some concentration of dark matter or structure we haven't accounted for? And here's an even deeper question. What does it mean that we're being pulled through space at such tremendous speeds? The Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the center of the Milky Way at about 230 kilometers per second. The Milky Way is falling toward the Great Attractor and Shapley supercluster at 600 kilometers per second. And all of this is in addition to the cosmic expansion carrying distant galaxies away from us. We are hurtling through space in multiple directions simultaneously, riding on a planet that orbits a star that orbits a galactic center that's falling toward a mysterious mass concentration, all while the universe expands. Does that change how you feel about standing still? Now I want to tell you about cosmic nomads, worlds that belong to no star, drifting alone in the darkness of interstellar space. We call them rogue planets, and they might outnumber stars in our galaxy. Think about that for a moment. Planets, worlds potentially as massive as Jupiter or as small as Earth, wandering the void with no sun to warm them, no light to guide them, invisible and silent. How did they get there? Some were ejected from their birth solar systems by gravitational interactions, flung out like stones from a slingshot when they passed too close to a larger planet or when their star system had a close encounter with another star. Others might have formed alone in space, condensing from clouds of gas and dust without ever being part of a planetary system. The first strong evidence for rogue planets came from gravitational microlensing surveys. When a massive object passes in front of a distant star from our perspective, its gravity bends the star's light, causing the star to temporarily brighten in a characteristic way. By analyzing these brightening events, astronomers can detect objects too dark to see directly, including rogue planets. Surveys suggest there could be billions or even trillions of rogue planets in the Milky Way, possibly more than twice as many rogue planets as stars. Our galaxy might be teeming with these orphaned worlds, invisible, traveling alone through the cosmic night. Imagine what such a world would be like. With no star to provide warmth, any surface would be frozen at temperatures just a few degrees above absolute zero. Any atmosphere would condense into ice or liquid and freeze solid on the ground. But here's where it gets interesting. Some scientists speculate that certain rogue planets might still harbor life. How? A large rogue planet with a thick atmosphere could retain internal heat from its formation for billions of years. Radioactive decay in the planet's interior could provide additional warmth. It's possible that beneath a thick layer of ice, a subsurface ocean could exist, kept liquid by tidal heating or geothermal energy. On Earth, we found life thriving in deep ocean vents, in complete darkness, powered by chemical energy rather than sunlight. Could similar ecosystems exist on rogue planets, buried beneath miles of ice, never knowing a sun exists? Here's a disturbing thought. Rogue planets are extremely difficult to detect, and they're moving through the galaxy. Could one pass through our solar system? The probability is low, but space is old and such events might have happened in the past. A rogue planet entering the solar system could gravitationally perturb the orbits of planets, potentially ejecting Earth from the Sun's orbit or sending it spiraling inward. Such an event would be catastrophic beyond imagination. There would likely be little warning. We might detect the intruder only when it was already disrupting planetary orbits. This scenario, while unlikely in any given million-year period, becomes more probable over the billions of years of the solar system's existence. Has a rogue planet ever passed nearby, causing some ancient disruption we've yet to recognize in the geological record? Some astronomers have speculated that a distant, undetected planet, sometimes called Planet 9, might exist in the far reaches of our solar system, shepherding the orbits of distant objects. Could this hypothetical planet be a captured rogue, An interloper from interstellar space that was gravitationally snared by the sun long ago? We don't know. The outer solar system is vast and dark, and a planet out there could remain hidden for centuries more. Imagine that, a world in our own solar system, orbiting our own sun, and we haven't found it yet. Let's shift to something that has puzzled astronomers since its discovery and might represent one of the most energetic phenomena in the universe. In 2007, astronomers detected a brief, intense blast of radio waves unlike anything seen before. It lasted just a few milliseconds, but in that tiny fraction of a second, it released as much energy as the sun emits in several days. This was the first fast radio burst, or FRB, and it came from billions of light years away. Since then, we've detected hundreds more. These bursts are among the most mysterious phenomena in astrophysics. The brief duration and immense distance of FRBs tell us something remarkable. Whatever causes them must be incredibly compact and powerful. If a source is varying on a timescale of milliseconds, it can be no larger than the distance light travels in milliseconds, just a few hundred kilometers. Yet these objects are pumping out more energy in a flash than our sun produces in days, all from a region smaller than Earth. What could possibly do this? The honest answer is we don't know for certain, but we have theories. Many astronomers suspect magnetars might be responsible for at least some FRBs. As we discussed earlier, magnetars have unimaginably strong magnetic fields and can release tremendous bursts of energy during starquakes. In 2020, for the first time, an FRB was detected coming from a magnetar within our own galaxy, SGR 1935 plus 2154. This was a breakthrough, providing the first clear link between FRBs and a known type of object. However, not all FRBs might have the same cause. Some repeat, sending out multiple bursts over time, while others appear to be one-time events. Some show strange patterns, like a source designated FRB 180916 that seem to follow a 16-day cycle of activity and silence. What could cause such regularity? Speculation runs wild when the data is limited. Some theories propose colliding neutron stars, others suggest evaporating black holes or strange physics involving cosmic strings, hypothetical defects in spacetime left over from the Big Bang. A few scientists have even entertained the possibility, however remote, that some FRBs could be artificial signals from advanced alien civilizations using powerful transmitters for propulsion or communication. This seems extraordinarily unlikely, but it highlights how little we understand about these bursts. When we don't know what something is, we can't completely rule out exotic explanations. Here's what keeps astronomers up at night. FRBs are being detected regularly now, which means they must be common in the universe. If every FRB we detect represents a cataclysmic event like a magnetar eruption or colliding stellar remnants, these events must be happening constantly across the cosmos. Or if some FRBs are repeating sources, perhaps they represent a phase in the life of certain objects that we haven't recognized. Every answer leads to new questions. Why do some repeat and others don't? Why do they show different patterns? What triggers them? And perhaps most intriguingly, what can they tell us about the universe between us and the source? As radio waves from an FRB travel across billions of light years, they pass through all the matter in between, all the gas, plasma, and magnetic fields filling the space between galaxies. This journey affects the signal in measurable ways, dispersing it and polarizing it. By carefully analyzing these effects, astronomers can use FRBs as probes of the intergalactic medium, mapping invisible structures and testing our models of the universe. In a sense, every FRB is a message from the distant universe, encoded with information about everything it passed through. We're learning to read these messages, and they're telling us about things we could never observe directly. Now, let me tell you about emptiness, but not just any emptiness. Imagine a region of space so vast and so empty that if Earth were at its center, we would see almost no galaxies in any direction for hundreds of millions of light years. This place exists. It's called the Boötes void, sometimes called the Great Nothing, and it's one of the largest known structures in the universe. Discovered in 1981, the VOID void is approximately 330 million light-years in diameter. To put that in perspective, our entire Milky Way galaxy is about 100,000 light-years across. You could line up 3,300 Milky Way galaxies edge to edge to span the VOID void. In such a volume, we would typically expect to find around 2,000 galaxies. In the VOID void, there are only about 60. It's almost completely empty, a cosmic abyss of unimaginable scale. How does such a thing form? According to our understanding of cosmic structure formation, matter in the early universe was distributed almost uniformly, with tiny variations in density. Over billions of years, gravity amplified these variations. Denser regions attracted more matter, growing into galaxy clusters and superclusters. Less dense regions lost matter to their denser neighbors, becoming voids. This process created a cosmic web, a foam-like structure of galaxy filaments and clusters surrounding vast voids. But the VOID void is exceptionally large and empty, even for a void. Why? Some cosmologists have speculated about unusual scenarios. Could there be something we don't understand about the initial conditions of the universe in that region? Could dark energy, the mysterious force accelerating cosmic expansion, have a different strength or behavior there? This seems unlikely, as all evidence suggests dark energy is uniform across the universe, but we can't rule it out entirely. A more exotic speculation, and this is purely theoretical with no supporting evidence, asks whether a void could be a kind of scar or remnant from the very earliest moments of the universe, perhaps even evidence of a collision with another universe in a multiverse scenario. This is wild speculation, far beyond our current ability to test, but it illustrates how such extremes in the cosmic structure challenge our understanding. What would it be like to live in a galaxy in the center of the VOID void? Imagine being on a planet there, looking up at the night sky. You would see the stars of your own galaxy, but beyond that, almost nothing. No other galaxies visible to the naked eye, possibly none visible even with telescopes depending on exactly where you were. The night sky would be profoundly empty, a void of blackness between the stars. Civilizations there might develop entirely different cosmological theories, perhaps thinking their galaxy was all that existed. It wasn't until the 20th century that humans realized other galaxies existed beyond the Milky Way. What if we had been in the VOID void? Would we have made that discovery? Would we understand the universe is expanding? Some of our most fundamental cosmological insights came from observing other galaxies. A civilization in a void might be starved of such data. This leads to an uncomfortable question. Are we missing crucial information about the universe because of where we happen to be located? We sit in a fairly typical part of the universe, in the outskirts of a spiral galaxy within a modest galaxy group. But might there be cosmic phenomena or structures visible only from other vantage points? Could a civilization in a different location see things we can't, leading them to different conclusions about reality? The universe might look very different depending on where you observe it from. There's another strange possibility that emerges from the mathematics of general relativity, something that has never been observed and might not even exist, but which represents one of the most peculiar theoretical predictions: white holes. If you're familiar with black holes, those regions where matter falls in and can never escape, then white holes are their time-reversed twins. A white hole would be a region of space-time where matter and light can only come out, never go in. Just as you can't escape from inside a black hole's event horizon, you couldn't enter a white hole's event horizon from the outside. Matter would be expelled outward from the center. How is this even possible? The equations of general relativity are time-symmetric in a certain sense. If you have a solution describing matter falling into a black hole and you reverse the direction of time, you get a solution describing matter emerging from a white hole. Mathematically, white holes are just as valid as black holes, but physically, they seem absurd. Where would the matter come from? How would a white hole form? The most common speculation is that white holes, if they exist, might be connected to black holes, with a singularity at the center of a black hole serving as a kind of one-way passage to a white hole in another region of space-time or even another universe. This is the idea behind wormholes, tunnels through space-time connecting distant points or separate universes. However, there are enormous problems with this idea. For one, the mathematics suggests that such wormholes would be unstable, collapsing so quickly that not even light could pass through. To hold a wormhole open, you would need exotic matter with negative energy density, something we've never observed and which might not exist. Even if wormholes could exist, it's not clear they would behave like the white holes predicted by time-reversing black hole solutions. Some physicists have proposed that white holes might have existed in the early universe, perhaps even that the Big Bang itself was a kind of white hole event. This is highly speculative. Others suggest that black holes might eventually become white holes, that the singularity at the center might be a region of extreme quantum effects that bounce matter back out after some enormous length of time, perhaps longer than the current age of the universe. Here's a thought experiment for you. If white holes exist somewhere in the universe, what would they look like? A white hole would be violently expelling matter and energy. It might appear as an incredibly bright, point-like source, perhaps mistaken for something else. Some scientists have speculated whether certain gamma-ray bursts, the most energetic explosions in the universe after the Big Bang, could be white hole events. This seems unlikely, as we have good alternative explanations for gamma-ray bursts involving supernovae and merging neutron stars, but it illustrates the challenge. If we saw a white hole, would we recognize it? Or would we interpret it as something more conventional? The lack of any convincing white hole candidates suggests they either don't exist, are extraordinarily rare, or look like something we've already explained another way. Most physicists suspect white holes simply don't occur in nature, that while the mathematics allows them, the actual conditions to create one might be impossible to achieve. This wouldn't be the first time a theoretical solution didn't correspond to reality. But the possibility lingers, a ghost in the equations, reminding us that the universe might yet have surprises. Let me tell you about another mind-bending aspect of the cosmos, something that emerges when we consider the universe at its largest scales. The observable universe has a boundary, not a physical edge, but an informational one. Because light travels at a finite speed and the universe has a finite age, there's a maximum distance from which light has had time to reach us. This boundary, about 46 billion light-years away in all directions, is called the edge of the observable universe. Beyond it, there could be more universe, possibly infinite in extent, but we can never see it. The light from those regions hasn't had time to reach us and never will because the expansion of space is carrying them away faster than their light can traverse the growing distance. But here's where it gets truly strange. As the universe continues to expand, and as dark energy drives that expansion to accelerate, fewer and fewer distant galaxies will remain visible to us. Right now, we can see galaxies from nearly the entire history of the universe. But billions of years in the future, those distant galaxies will have receded beyond the cosmic horizon. Their light, stretched to infinite wavelengths by expansion, will fade away. Eventually, beings living in the far future, trillions of years from now, will look out and see only the galaxies in their local group, all the others having vanished beyond the horizon. They will see a much smaller, much emptier universe than we do. And here's the really disturbing part. Without evidence of distant galaxies, without the cosmic microwave background radiation that will have redshifted into undetectability, future scientists might have no way to discover that the universe is expanding, no way to infer the Big Bang ever happened. They might think their local galaxy group is the entire universe, eternal and unchanging. They would be profoundly wrong about the nature of reality, not because they're bad scientists, but because the evidence would no longer be accessible. The universe would have erased its own history. This should make you ask, what evidence are we missing? What crucial facts about the universe have already been erased by time and expansion? Truths that were discoverable to observers in the distant past but are lost to us now. Are we drawing incorrect conclusions about the cosmos because we're missing information that no longer exists in any observable form? It's a humbling thought. We pride ourselves on the scientific method, on following evidence wherever it leads. But what if some of the most important evidence has already vanished? There's a concept in cosmology called the anthropic principle, which in its weakest form simply states that our observations of the universe are biased by the fact that we exist to observe it. We live in a time and place where conditions allow for complex chemistry, planets, and life because those are the only conditions in which observers like us can arise. But there's a stronger form of the anthropic principle that some find troubling. It suggests that the universe's properties, the strength of fundamental forces, the mass of particles, the amount of dark energy, all seem finely tuned to allow for the existence of stars, planets, and ultimately life. Change any of these values by even a small amount, and the universe would be sterile, unable to form the structures necessary for complexity. Why is the universe this way? One answer, the multiverse hypothesis, proposes that our universe is just one of countless universes, each with different properties. Most of those universes are lifeless, but we necessarily find ourselves in one of the rare universes where the conditions are right for life. We're here because we couldn't be anywhere else. This answer is deeply unsatisfying to many scientists because it seems untestable. If other universes exist but are completely disconnected from ours, how could we ever gather evidence for them? Yet some versions of multiverse theory do make testable predictions, or at least predictions that are testable in principle if not in practice with current technology. For instance, if our universe is part of an eternally inflating multiverse, where regions of space undergo rapid inflation to become separate universe bubbles, then collisions between bubbles might leave imprints in the cosmic microwave background radiation. Researchers have looked for such signatures and haven't found any, but that doesn't rule out the idea. The universe is large, and we can only observe a portion of it. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that every quantum measurement spawns multiple universes, one for each possible outcome. This interpretation is controversial and might be fundamentally untestable, but it's taken seriously by some physicists because it solves certain conceptual problems in quantum mechanics without adding any new assumptions beyond taking the mathematics at face value. The question of the multiverse touches on deep philosophical issues. What does it mean for something to exist if it can never be observed? Is a theory scientific if it can't be tested? Some argue that multiverse theories are more philosophy or metaphysics than physics. Others contend that if a theory makes successful predictions about things we can observe and happens to also predict unobservable things, that doesn't invalidate it. These debates continue, and they matter because they get at the heart of what science is and what it can tell us. Let me bring us back to something we can observe, something that challenges our understanding in a different way. In 2015, the LIGO Observatory detected gravitational waves for the first time, ripples in the fabric of spacetime itself produced by the merger of two black holes more than 1 billion light-years away. This was a triumph of physics and engineering, confirming a prediction Einstein made a century earlier. But it also opened a new window on the universe. Before gravitational wave astronomy, we studied the cosmos almost exclusively through electromagnetic radiation, light, radio waves, X-rays, gamma rays. Now we can detect events through space-time vibrations, and we're seeing things we never could before. Gravitational waves are produced by accelerating masses, but they're incredibly weak. It takes cataclysmic events, like merging black holes or neutron stars, to produce waves strong enough to detect across cosmic distances. When LIGO detected that first merger, the gravitational wave passing through Earth stretched and squeezed space by less than 1/10,000th the width of a proton. The detectors are so sensitive they can measure changes in distance smaller than an atomic nucleus over laser path lengths of several kilometers. This is like measuring the distance from Earth to the nearest star to within the width of a human hair. Since that first detection, dozens more have been found. We've detected merging black holes of various masses, merging neutron stars, and possibly even mixed mergers between a black hole and a neutron star. Each detection tells us something new. The neutron star merger detected in 2017, designated GW170817, was particularly remarkable because it was also observed with traditional telescopes. When the neutron stars collided, they produced gravitational waves, a gamma-ray burst, and a kilonova, an explosion that synthesizes heavy elements like gold and platinum. For the first time, we witnessed such an event from multiple perspectives, combining gravitational wave data with electromagnetic observations. This ushered in the era of multi-messenger astronomy. What did we learn? Among other things, that merger confirmed that neutron star collisions are a major source of heavy elements in the universe. The gold in any jewelry you own, the platinum in catalytic converters, the uranium in nuclear reactors, much of it was forged in the unimaginable violence of colliding neutron stars and scattered into space to eventually be incorporated into new stars, planets, and yes, even into you. You are made of star stuff, as Carl Sagan famously said, but more specifically, you're made of cataclysm, of the deaths and collisions of stars. Gravitational wave astronomy is still in its infancy. Future detectors, more sensitive and located in space, will detect waves from farther away and from less massive sources. We might detect gravitational waves from the Big Bang itself, created in the first moments of cosmic inflation. Such a detection would be transformative, providing a window into the universe's first fraction of a second, long before any light could travel freely. What will we find as we listen more carefully to spacetime's vibrations? What sources have we not imagined? The history of astronomy tells us that whenever we observe the universe in a new way, we discover unexpected things. Here's something to consider. Gravitational waves travel at the speed of light, and like light, they're affected by the expansion of the universe and by the mass they pass near. But unlike light, gravitational waves interact incredibly weakly with matter. They pass through planets, stars, even black holes, barely noticing. This means a gravitational wave we detect today has traveled across the universe virtually unimpeded, carrying information from the source that hasn't been absorbed or scattered. In principle, we could detect gravitational waves from the very edge of the observable universe with minimal distortion. As our detectors improve, we might map the universe's history in gravitational waves, observing events that left no electromagnetic signature. Think about what that means. There could be entire classes of cosmic events that are invisible to traditional astronomy but visible in gravitational waves. We've already found that stellar mass black hole mergers are more common and involve more massive black holes than many predicted. What else is out there, happening constantly, that we've simply never been able to see? What if there are objects or phenomena that only interact gravitationally, producing no light or other radiation? We would be completely blind to them except through their gravitational effects. Dark matter might fall into this category. If dark matter is made of primordial black holes, their mergers would produce gravitational waves with specific characteristics. Searches for such signals are ongoing. Let's consider something even more speculative, the possibility of cosmic strings. These are hypothetical one-dimensional defects in spacetime, like cracks in ice as it freezes, formed during phase transitions in the very early universe. If they exist, cosmic strings would be incredibly thin but immensely dense, with tensions comparable to the energy scales of the early universe. A cosmic string stretched across the galaxy would be thinner than an atom but would weigh more than the sun. Such an object passing near Earth would cause devastating gravitational effects, distorting spacetime and potentially affecting planetary orbits. Fortunately, if cosmic strings exist, they're thought to be rare, and space is vast. But here's the interesting part. Cosmic strings, if they exist, would oscillate and radiate gravitational waves with specific patterns. Current gravitational wave detectors are searching for such signatures. So far, nothing has been found, which places limits on how common cosmic strings could be. But the search continues, and a detection would be revolutionary, providing direct evidence of physics from the first moments after the Big Bang. This is one of the remarkable things about modern cosmology. We can test theories about the universe's first fraction of a second, conditions so extreme they make neutron stars look tame, by making observations today. All of this brings us to a profound realization. The universe is not only stranger than we imagine, it's stranger than we can imagine. Our brains evolved to navigate a world of medium-sized objects moving at moderate speeds, where quantum effects are negligible and space-time curvature is imperceptible. We have no intuition for black holes, quantum entanglement, dark energy, or any of the other phenomena we've discussed. Every one of these things defies common sense. Yet through mathematics, experimentation, and observation, we've been able to understand them, at least partially. We've built theories that make predictions, and we've tested those predictions. The fact that we can do this at all is astonishing. But let me ask you this. Are there limits to what we can understand? Are there aspects of reality that are simply beyond human comprehension, not because we lack the data, but because our minds are not equipped to grasp them? Some physicists speculate about this. Just as a dog can't understand calculus not because dogs are lazy, but because their brains lack the necessary architecture, might there be concepts in physics that human brains are fundamentally unable to fully comprehend? We might be able to manipulate the mathematics, make predictions, and verify them, but perhaps we can't truly understand what the math is telling us about reality. String theory is sometimes cited as an example. This theoretical framework attempts to unify quantum mechanics and general relativity by proposing that fundamental particles are actually tiny vibrating strings, and that the universe has more dimensions than the 4 we experience. Some versions require 10 or 11 dimensions. Mathematically, the theory is rich and beautiful, and it has led to insights in other areas of mathematics and physics. But it makes few testable predictions, and many physicists question whether it's even science in the traditional sense. More to the point, almost no one, including the theory's practitioners, claims to have a good intuitive grasp of what 10-dimensional space-time actually is. We can work with the math, but we can't visualize or conceptualize it in the way we can visualize 3-dimensional space. Is this a limit of our imagination, or is there simply nothing to understand beyond the mathematics itself? Some argue that demanding intuitive understanding is asking too much, that at the frontiers of physics, the math is the understanding. The universe doesn't owe us an explanation that makes sense to our primate brains. It simply is what it is, and if we can describe it mathematically, that's enough. Others find this unsatisfying, arguing that true understanding requires more than successful calculation. These are not idle questions. They touch on the nature of knowledge, the limits of science, and what it means to understand something. And they remind us that for all we've learned, we remain profoundly ignorant. We don't know what dark matter is. We don't know what dark energy is. We don't know if the universe is finite or infinite. We don't know if there are other universes. We don't know if our theories of physics break down in conditions we haven't tested yet. We don't know if we're alone in the universe or if life is common. We have hypotheses and theories, but vast uncertainties remain. And that brings me to perhaps the strangest thing of all, a question that encompasses all the others. Why is there something rather than nothing? Why does the universe exist? This is the most fundamental question we can ask, and it might be unanswerable. Some physicists have tried to address it. Lawrence Krauss wrote a book titled A Universe from Nothing, arguing that quantum mechanics allows universes to spontaneously appear from vacuum fluctuations, that nothing is unstable and will inevitably produce something. But critics point out that the quantum vacuum he describes isn't really nothing. It's a seething sea of virtual particles governed by quantum field theory, which presupposes space, time, and physical laws. Why does quantum field theory exist? Why those laws and not others or none at all? Stephen Hawking and James Hartle proposed the no-boundary hypothesis, suggesting that time itself might be finite in the past but without a boundary or beginning, by imagining time becomes space-like in the very early universe. In this view, asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because there's no before. Time itself has a structure that avoids the singularity. This is mathematically elegant but difficult to test and doesn't fully answer why the universe exists. Some turn to philosophy or theology for answers, proposing that a necessary being or principle grounds existence. Others suggest the question might be malformed, that our notions of cause and explanation break down when applied to the totality of existence. Maybe the universe doesn't have a reason. Maybe it just is, a brute fact, and our desire for explanation reflects our parochial experience where everything has a cause, but that pattern doesn't extend to reality as a whole. These are deep waters, and they're perhaps beyond the scope of science as traditionally understood, but they loom in the background of cosmology. When we trace the universe back to the Big Bang, we find a point where our theories fail. General relativity predicts a singularity, but we know that description must break down. A theory of quantum gravity, which we don't have yet, would be needed to describe that regime. Even if we had such a theory, it might just push the mystery back further. Why that theory? Why any laws at all? Here's what we're left with: a universe of breathtaking strangeness, filled with phenomena that challenge everything we thought we knew. Black holes that warp space-time into prisons from which not even light escapes. Invisible matter and energy comprising the vast majority of existence. Quantum entanglement connecting particles across cosmic distances instantaneously. Neutron stars and magnetars squeezing matter into unimaginable densities and generating fields that tear at the fabric of reality. Mysterious attractors pulling galaxies through space. Rogue planets wandering the darkness between the stars. Fast radio bursts flashing across the cosmos from unknown sources. Voids of nearly incomprehensible emptiness. Theoretical white holes that might expel matter as black holes consume it. And underlying all of it, gravitational waves rippling through space-time, carrying messages from the most violent events in cosmic history. Each of these phenomena is strange in its own right, but taken together, they paint a picture of a universe that is wilder, more dynamic, more mysterious than the orderly celestial sphere imagined by ancient philosophers. We live in a cosmos where the impossible is routine, where extremes beyond human experience are commonplace, where every answer reveals deeper questions. And perhaps most remarkably, we've figured out how to study these things. Creatures who evolved on a small planet orbiting an ordinary star have reached out with mathematics and machines to probe the universe's deepest secrets. But our knowledge remains fragmentary. For every question we've answered, new ones emerge. The more we learn, the more we realize how much we don't know. This should fill us with humility, but also with excitement. We live in a time when gravitational waves have just been detected, when new telescopes are revealing planets around other stars, when we're sending robots to explore our solar system and planning to return to the moon and reach Mars. We're on the cusp of discoveries that will reshape our understanding of reality. What will we find as we peer deeper into space and time? What surprises await in the data streaming back from our instruments? Consider this: every strange thing we've discussed was unknown to humans for most of our history. Black holes were first theorized in the 20th century and confirmed observationally even more recently. Dark matter and dark energy were discovered in just the last few decades. Quantum entanglement was demonstrated conclusively in the late 20th century. Neutron stars were predicted in the 1930s and discovered in the 1960s. Gravitational waves were detected for the first time less than a decade ago. Our knowledge of the universe's strangeness is new and growing. What will we know in another century? What phenomena do we currently have no inkling of? And here's a final thought to leave you with. All of this strangeness, all of these cosmic wonders, they're not separate from you. You are made of atoms forged in stars, scattered by supernovae and neutron star collisions. Your body contains elements created in some of the most violent events in the universe. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were synthesized in stellar furnaces and cast into space by dying stars. You are not merely in the universe. You are of it, a part of the cosmos contemplating itself. More than that, The same physical laws that govern black holes and quantum fields govern the atoms in your body. The same forces are at play. In a very real sense, you are stardust arranged in such a way that you can think, feel, and wonder about the universe that created you. That's perhaps the strangest and most wonderful thing of all. The universe is not just something we observe from the outside. We are part of it, a way for the cosmos to know itself. So when you look up at the night sky, remember, you're seeing light that has traveled across vast distances, across years or centuries or millennia, from stars both living and dead. You're seeing a universe filled with wonders beyond imagination, with black holes and dark matter, with neutron stars and cosmic voids, with phenomena we've discovered and others we haven't yet dreamed of. You're connected to all of it through the very substance of your being. And that should fill you with a sense of awe, a recognition that we live in a strange, beautiful, terrifying, magnificent cosmos that we're only beginning to understand. The universe keeps its secrets well, but slowly, painstakingly, we're learning to read its language, to decipher its mysteries. Each discovery is a hard-won victory against ignorance, a light kindled in the darkness of our not knowing. And there's so much more to discover, so many more questions to ask, so many more wonders waiting to be found. The strangest things in the universe aren't just objects or phenomena. They're invitations, calls to curiosity, challenges to push the boundaries of human knowledge further into the unknown. Will you accept the invitation? Will you look up and wonder? Will you seek to understand? Because the universe is stranger than we can imagine, and that's what makes it worth exploring.